So let me see. I will wait a second. So this talk is an exploration of the projective sets of reals under the axiom of projective determinacy or large cardinals. So this is out of battery. So this is the definition of projective sets. Just to remind you, so the reals, the irrationals of reals are homeomorphic to omega, and a set of reals is sigma 1n if it's sigma n definable over the set theoretic structure phi omega plus 1. So this is light phase sigma 1n, and this is sigma 1n relative to a parameter. And it's bold phase sigma 1n if and only if it's sigma 1n from a real parameter. So there is an equivalence definition without the set theory. So it is sigma 1 if it is a projection of a two-dimensional Borel set. And it's pi 1n if its complement is sigma 1n, and it's sigma 1n plus 1 if it's the projection of pi 1n set. So the projective sets is the smallest collection of sets of reals which contains all the Borel sets and closed under complements and projection. So we will regard projective sets as the simplest sets of reals. And so, for example, we know that there exists a big non-measurable set, but the proof uses a very strong form of the axiom of choice. And our intuition will say, well, obviously every easily definable set of reals should be a big measurable. So in particular, the simplest sets will be projective sets. And so obviously this meets our intuition that every projective set is a big measurable. So in particular, V is not equal to L. And so by the way, this is a consequence of the axiom of projective determinacy. And similarly, we have other regularity properties of projective sets. For example, the Baire property or the perfect set property, which is the effective version of continuum hypothesis. So every subset of reals, if it's simple enough, it must be either countable or have the same cardinality with the whole set of reals, and and there is a projective bijection in between. So assuming large cardinals, projective determinacy, we can get a complete answer to most of those interesting questions in mathematics in the effective sense. And as I just mentioned, there is a strong influence of large cardinals onto the set of reals. So assuming there are n wooden cardinals below a measurable, we get a certain degree of determinacy of pi 1n plus 1 sets. So this is one of the surprising facts about large cardinals. So these large cardinals have nothing to do with the real numbers. It is really higher up, but it still has an influence on the set of real numbers. So all those elementary embeddings about the large cardinals have critical point way above omega plus 1. But they really decided the behavior of projective sets of reals. And if you assume more wooden cardinals, you will get the determinacy of more sets of reals. So in this talk, we will assume enough large cardinals so that the sets of the projective sets or the sets of reals in L of R are determined. So the typical way of getting the regularity property of a set of reals is by the tree representation. So a tree on omega times x is a subset of finite strings, and both coordinates have equal length closed under initial segments. So we define the infinite branches in the usual way, and the projection of T is a set of reals, so that x is in the projection of T, if and only if there is a second coordinate alpha sequence witnessing that x alpha belongs to the infinite branches of T. So this is the Suslin representation, and we define a set of reals to be lambda Suslin if it is the projection of a tree whose second coordinate is on this ordinal lambda. So it is Suslin if it is lambda Suslin for some lambda. So some classical results that sigma 1 sets are omega Suslin. So it is a projection of a tree essentially on omega. And the light phase sigma 1 sets will be effectively Suslin, so the tree will be effectively computable. And well, this definition is not extremely useful because we have the axiom of choice. Actually, every set of reals is Suslin. The problem is that this fact, again, uses a very strong form of the axiom of choice. So it is not effective. So in particular, it doesn't settle the question about, let's say, the effective version of continuum hypothesis or the big measurability of projective sets. So, the the correct approach of analyzing the Suslinness of a set of reals is we want more information about the tree. So we would like to get the different degrees of Suslinness on different degrees of sets of reals. And yeah, so this is the question about the effective version. So the complexity of the tree which projects to A will depend on the complexity of A. And so this talk will be, well, one of the topics will be to analyze the complexity of the tree T instead of just coming from a well-ordering of the reals. So we want some degree of effectiveness. So let's see. So a good test question about the effectiveness of the tree representation is, well, you can think of in pure mathematical terms. If there is a set of reals which is non-empty and has a certain property, then it must have a member with that property. So let me say again. So if there is a real number with a certain property, then there must be a real number with a minimum complexity. So in particular, every non-empty sigma 1 set contains a real which is recursive in cleanness O, which says, well, if there is a real number with a certain sigma 1 property, then you can find a witness whose complexity is bounded by cleanness O. And similarly, if a sigma 1,2 property about reals has a witness, there must be a witness whose complexity is delta 1,2 as a subset of omega. And from inner model theory, we get the basis theorem for sigma 1,3 sets, assuming large cardinals. So every non-empty sigma 1,3 set has a member recursive in this mouse called M1 sharp. And so forth. So sigma 1,4 will be have a basis of delta 1,4 and so forth. So the descriptive set theoretic proof of these facts is via the Suslin representation of the set. So assume we have a set of reals A, which is non-empty, and it has a certain property. So, well, we represent it in terms of a projection of a tree. And we pick the leftmost branch. So it's the leftmost branch, and so the definition is the obvious way. So if there is another branch, then the drawing of the two coordinates is minimum one. So all these basis theorems can be proved by this view of the descriptive set theoretic view. So the central problem is to analyze the complexity of the tree. So by the way, this is the leftmost real associated to the leftmost branch. I should have mentioned it. So just now, a few slides ago, I said that sigma 1 sets, they are omega Suslin. And going one level up, sigma 1 sets, they are omega 1 Suslin. And the tree is usually called the Schoenfield tree, which gives absoluteness between sigma 1 absoluteness between proper class transitive models. And there is a good notion of effectivity on a tree whose second coordinate is omega 1. And the reason is there is a good coding mechanism of ordinals up to omega 1, which is the countable ordinals. So WO is the set of reals which codes a well ordering. So every infinite countable ordinal is coded by a real, and this coding set is pi 1, 1. And so the Schoenfield tree is I think basically is both sigma 1, 1, there's an optimal optimal approximation on the trees projecting to sigma 1, 2. And so the next goal is to characterize the sigma 1, 3 sets. So is to give an effective Suslinist representation of sigma 1, 3 sets. So this is a result essentially by Solovay that assuming large cardinals, sigma 1, 3 sets are U omega Suslin, where U omega is an ordinal bigger than omega 1. It comes out of inner model theory, and this is the optimal ordinal in the sense of effectiveness. So now we are ready to define what we mean by the uniform indiscernible. So it comes out of inner model theory, or essentially the theory of sharps for L and L relative to reals. So assuming large cardinals, there is a club class of indiscernibles for L, which is a club class of ordinals C alpha indexed by alpha, which Skolem generate L, and they are order indiscernibles in the sense that the truth value of the sequence depends only on the ordering of their subscripts. And this set is closed under the option. So this is a canonical set of indiscernibles, which is usually called the silver indiscernibles. And from that we can extract a real number, zero sharp, which is the drawing of the theory of finitely many of those indiscernibles. Oh, by the way, in particular, every uncountable cardinal must be one of those indiscernibles. So zero sharp itself is a large cardinal axiom which asserts the existence of a well-founded, remarkable EM blueprint which gives an elementary embedding from L to L. So from descriptive set theory, we need the EM blueprint definition of zero sharp, because we will need the EM blueprint formulation to get a nice coding of ordinals up to U omega. So I guess many people are familiar with EM blueprints, so I'm quickly recalling the theory. So an EM blueprint is a complete consistent theory for in the language with set theory and constant symbols of order type omega. And they are ordered, and it satisfies V equals L. And they are indiscernibles, namely the truth values only depend on the order of their subscripts. And so zero sharp is axiomatizable in terms of an EM blueprint. It is the unique, well-founded, and remarkable EM blueprint. So remarkability is some syntactical property called the remarkability axiom. And for every EM blueprint, for every linear ordering, there is a unique model. This comes out of the model theory, which is, so this is called the EM model. And it contains those points coming from those well-ordering on the set, so that this model is Skolem generated by those points, and it satisfies the crosses in the EM blueprint. So this is the EM model, as many people are familiar with. And an EM blueprint is well-founded if for every countable well-ordering, the EM model is also well-founded. So well-foundedness of an EM blueprint is pi12. Therefore, so this is the classical result that zero sharp is the unique, well-founded, remarkable EM blueprint. So it is a pi12 singleton. So the complexity comes from well-foundedness. And we can relativize to a real number. So coming back to the definition of uniform indiscernibles. So for every real X, we have a club class of silver indiscernibles. We intersect all those club classes over all reals. We get this uniform indiscernibles, which is also closed under the order topology and contains all the uncountable cardinals. So the first of them is U1, which is equal to Aleph1. And since it's closed, U omega should be the sup of UNs. So I mentioned that every sigma 1,3 set is U omega Suslin. And this is the optimal ordinal. U omega is the optimal ordinal in terms of the complexity. And the complexity is characterized in terms of the sharp codes. So a sharp code is a pair, so a Skolem term followed by X sharp for some real and a Skolem term, so that the Skolem term evaluated in Lx acting on some of the silver indiscernibles is an ordinal. And we have a coding, a canonical coding of ordinals in below UN+1, which is this sharp code tau X sharp should code this ordinal. We evaluate tau in Lx from those uniform indiscernibles. So this is our effective coding of ordinals in below U omega. So we can show that every ordinal has a code every ordinal below u omega has a code. And the set of sharp codes is pi12 because to say it's x sharp is pi12. And to identify whether two sharp codes are equal or to compare if one is smaller than the other is delta 1, 3. And this is also the optimal complexity. And well, just now so the first omega plus 1 many uniform indiscernibles are in our attention, and the descriptive set theoretic approach of viewing those indiscernibles is the projective well-ordered cardinalities. So, well, everybody knows that kappa is a cardinal if it's impossible to find a surjection from alpha onto kappa for alpha smaller, and we would like to state the effective version of the well-ordered cardinality. So an ordinal is a projectively well-ordered cardinal if it's impossible to find any alpha and a coding of alpha. So it is a surjection from rho onto alpha. So this is so we view this as a coding of alpha and another coding of kappa, and a surjection from one coding of alpha onto the coding of kappa, which is invariant in the codes. So this is the effective version. I think I ignored the projective. So yeah, so in between there, I should say there are no projective surjections. I mean, so the codes are projective, so that you can get this surjection from a smaller ordinal onto a bigger one. It turns out that those uniform indiscernibles are just an initial segment of those projectively well-ordered cardinals. So the first omega uncountable projectively well-ordered cardinals are just those uniform indiscernibles. So let's recap. Well, we can define the projectively well-ordered cardinalities, which seemingly doesn't use any inner model theory. It's purely, descriptive set theoretical. But to get a deep understanding about those projectively well-ordered cardinals, we need inner model theory. We need indiscernibles for L. And only then we can get a clear understanding about the first omega many projectively well-ordered cardinals. So this is, this is one instance that inner model theory is extremely useful into descriptive set theory, although the results are seemingly completely irrelevant. So, and more characterizations of the projectively well-ordered cardinalities. Well, we can define the projective successor in the obvious way. So we know that U omega is the sup of those uniform indiscernibles for finite n, and its successor is actually delta 1, 3, which is the sup of the order types of delta 1, 3 pre-well orderings of the reals. And to understand this fact and to trying to push this further into the projective hierarchy, the only fundamental way is to go through inner model theory and looking at various canonical structures arising out of the characterization from descriptive set theory. So once again, this is this is for sigma 1, 3. So yeah, sigma 1, 1, 3 is a projection of pi 1, 2. So sigma 1, 3 set is the projection of a tree on u omega, which is delta 1, 3 in the sharp codes. And the tree for pi 1, 2 is usually called the Martin-Soloway tree. And the definition of Martin-Soloway tree comes from, again, inner model theory, and in particular, the uniform indiscernibles. So for every order-preserving map, sigma, we can define an order-preserving map from in between those uniform indiscernibles by shifting the sharp codes. And we can show this is well-defined. And we get the Martin-Soloway tree, which comes out of the blueprint formulation of sharps. So this slide is a definition of the Martin-Soloway tree. We fix an effective list of Skolem terms. And we have a tree on 2 to less than omega, whose infinite branches is the set of remarkable EM blueprints over a real number. So, well, this is a pi 0, 1 statement to say well, it's Gödel complete. And we put this tree, we put S and alpha vector into the Martin-Soloway tree if the first coordinate eventually will be a remarkable EM blueprint, and the second coordinate is trying to prove that the EM blueprint is well-founded. So this is the definition of the Martin-Soloway tree, and the second coordinate is on u omega. So this T2 projects exactly to the set of sharps over some reals, and from that and Schoenfield absoluteness, we get it's easily to make a variant of T2 so that it projects to the universal pi 1, 2 set. And this is how we get the Suslin representation for sigma 1, 3 sets. And so concerning the degree of effectiveness, it is delta 1, 3 in the sharp codes. And this is an old notation from Q theory, the leftmost real. So it's the leftmost, the first coordinate of the leftmost branch of the T2 is called Y03. And this is the canonical real. So it turns out that, well, this T2 coming from the uniform indiscernibles and the leftmost branches, it is effectively equivalent to something from inner model theory, which is called M1 sharp. And this is many one equivalent. So we're equivalent by acquiring only one value. So once again, so this Y03 is the leftmost real coming from the Martin-Soloway tree construction, and in particular coming from the indiscernibles for L. And on the right-hand side, this M1 sharp is the least mouse which has a measurable and a wooden below the measurable. So it is a mouse with a wooden cardinal and a measurable. So this equivalence again highlights the importance of inner model theory in descriptive set theory. Well, if you want to, you are trying to understand the leftmost branch, but this is effectively just a mouse with a wooden cardinal, and the equivalence is really effective. It asks us only one value for the Turing equivalence. And this equivalence is needed to push the Martin-Soloway tree to the higher levels. Okay, so yeah, so maybe it is a bit helpful to assume AD, and we work in L of R, which is a model of AD, where the UNs are the first few cardinals, and the next one is delta 1, 3 is the successor of U omega. So delta 1, 3 is the successor of U omega, and the coding is via Kilnan's coding of subsets of U omega. So there is a section from reals to the power set of U omega, so which is whose complexity is delta 1, 3. And from this surjection, I can get a coding for every subset of U omega. So I can get a code for every subset of U omega from a real number using this surjection. And we can call this set WO3. And this set is the higher level analog of WO, which is the code of ordinals below omega 1. So now we have a picture. So for codings of ordinals below omega 1, we use the reals that code a well ordering of omega. And the similar pattern repeats between U omega and delta 1, 3. So every ordinal in this red interval is coded by a real number, and using this surjection, becoming a subset of U omega. And we can show that there are many analogies in between this red interval and the interval below omega 1. And the similar pattern will repeat to the higher levels, which is in between something called lambda 5 and delta 1, 5. And there is a periodicity of order 2. So in this blue interval, between U omega, between omega 1 and U omega, we just introduced the sharp codes for ordinals in this interval. And this pattern will also repeat itself between delta 1, 3 and lambda 5. So the coding will look exactly like the sharp codes for ordinals below U omega. And this is what I call the higher level sharp coding. And so this periodicity of order 2 will propagate all the way through the projective hierarchy. So yeah, so once again, delta 1n is the sup of the order type of pre-well orderings of delta 1n. And we have these, assuming large cardinals, they are all projectively well-ordered cardinals. And of course, there are more in between. So we get the optimal Suslin representation for sets of complexity pi 1 to n plus 1. And moreover, Jackson computes this the exact value of those projective ordinals in the Aleph sequence. Well, in our context, we will show that this projective ordinal we will identify the position of this projective ordinal in the sequence of projectively well-ordered cardinalities, assuming projective determinacy in V. And the result will exactly look like this. So in particular, delta 1, 5 will be this much. So it will be the omega to omega to omega plus 1 projective well-ordered cardinal. And moreover, inner model theory will provide a deep structural theory of those projective ordinals. So the last factor is dual to the fact about the pi 1 to n plus 1. So pi 1 to n is lambda to n plus 1 Suslin, where the lambda ordinal is the predecessor that I had in the previous slide. So in particular, lambda 5 is the predecessor, the projectively well-ordered predecessor of delta 1, 5. So now here comes some canonical structures. So we have a model theoretic form of pi11 sets. So pi11 is equivalent to sigma 1 over the least admissible set. So it is a uniform sigma 1 definition, and X satisfies this pi11 fact if you look at the minimum admissible set containing X, and it will satisfy this sigma 1 fact. And from there, we get this cleanest O, which is the collection of true sigma 1 sentences. Now going 2 levels up, the result looks exactly like the previous level. So a set of reals is pi13 if it is sigma 1 over this structure. So this L kappa 3 T2x is the minimum admissible set containing T2 and X. So the philosophical idea is that there are 2 additional quantifiers in this pi13 definition, and the 2 quantifiers are absorbed in this T2, which is the Martin-Soloway tree, and it comes out of the blueprint formulation of Sharpe's for reals. So this is we can view this pi13 fact as we can view this formulation as the normal form for pi13 sets. So it is sigma 1 over the least admissible containing T2. And similarly, we can define the higher level cleanest O. So, the slight difference is that omega becomes U omega, so the higher level will be essentially a subset of U omega, which is the true sentences, true sigma 1 sentences with one free variable alpha below U omega. So what I define as the 0-2 sharp, 0-2 sharp comes from this higher level analog of cleanest O. So we know it is essentially a subset of U omega, and we partition OT2 into omega many pieces, which is OT2 intersect omega times UN, and we squeeze the second coordinate of this object by looking at the least witness. And this will be the nth fragment of 0 sharp. So this is our way of squeezing this object, OT2, the fragment of OT2, into a real. And every real will be a fragment of 0-2 sharp. So in the end, 0-2 sharp will be the join of those pieces. So, 0-2 sharp is essentially just another formulation of the leftmost branch of T2. And this will turn out to be M1 sharp, effectively. So once again, this definition has no mention of wooden cardinals or extended models, just uniform indiscernibles. But in the end, it is equivalent to some inner model theory. So it is again a strong evidence that inner model theory provides deep insight into higher level descriptive set theory. So to the higher level, there is again a canonical tree called T3, which comes from the Suslin representation for pi13 sets. It's coming from essentially the Moskowakis periodicity. And this canonical structure, LT3, is invariant of the choice of our definition of T3 if we formulate it correctly enough. And once again, this tree T3 comes from the proof of determinacy. But if you look at this structure, if we want to understand this structure better, well, there is a way, and it comes from inner model theory again. It is just, so by a theorem of Steele, LT3 is just a mouse. And it comes from iteration of iteration of M2 sharp, which is a mouse with a sharp and 2 wooden cardinals. So to go higher up, we would like to get an analog of the Martin-Soloway tree, which provides a coding for all the ordinals below u omega. We want to push this level up, and the correct analog will be some kind of indiscernibles for the structure LT3. So this is what I call the level 3 indiscernibles of LT3. And this will be effectively equivalent to M2 sharp, which is the least mouse with a sharp and 2 wooden cardinals. So yeah, so this is how I started my talk. We had those effectively well-ordered cardinals, and we had the Martin-Soloway tree, and the model theoretic form, and we know that we need an effective coding of all the ordinals in u omega to speak about the effectiveness of the trees, and we want to generalize this whole picture to the higher level. So the generalization will be, we will get more effectively well-ordered cardinals above delta 1, 3, and they will have order type omega 2, omega 2, omega. We will similarly get an effective coding of all the ordinals in this, what I call the higher level uniform indiscernible, and the higher level analog of the Martin-Soloway tree, which projects to the pi 1/4, and the similar things as the lower levels. So a level 3 EM blueprint will somewhat look like the EM blueprint for L. It is the it is a finite function. So it is a level 3 EM blueprint is a function whose domain is the set of some technical terms called the tree of uniform cardinalities, and so for every tree, this technical tree, the blueprint sends this tree to a complete consistent theory, and the theory will look like the theory of L delta 1, 3 of T3. And the theory will describe something which generalizes ZFC plus V equals L. So it will say that ZFC plus V is the core model plus I am a too small mouse, and there is a fixed pair of formulas which witness which projects to the universal pi 1 sigma 1 3 set and the universal pi 1 3 set, and they are correct about the M1 sharp operator, and finally something about the higher level indiscernibles. And similarly to the lower level, we get an EM model associated to this EM blueprint. And we would like to have something similar to indiscernibility. So, well, now it is of course more complicated. It's more than order indiscernibility, and there is some syntactical formula which is called remarkability, and the higher level analog of remarkability for pi12 is what I call the iterability, so which is a pi14 condition, which says if something pi13 happens, then the direct limit will be a pi13 iterable mouse. So the characterization heavily relies on inner model theory, and in the end it helps to characterize all the ordinals below lambda 5, which is a longer interval, and eventually from this EM blueprint formulation we get an effective codings of all the ordinals below delta 1,3 and delta 1,5. So similarly, we can show that there is a unique level 3 EM blueprint, and the blueprint is effectively equivalent to the least mouse with a sharp and 2 wooden cardinals. So the proof uses the proof of the lower level equivalence, which is the leftmost branch equivalent to a mouse with a 1 wooden cardinal. So we have those, from those blueprint formulation of the level 3 sharp, we can define the level 3 indiscernibles, which looks like and we have a coding system for ordinals below those higher level uniform indiscernibles, which looks like the coding of ordinals below u omega. It is just a Skolem term plus a sharp and plus some technical term. And from there, we can similarly define T4. It is the level 4 Martin-Soloway tree, which generalizes the level 2 Martin-Soloway tree. And so we return to this picture that the red intervals, so we get an effective coding for those red intervals that generalize the WO coding, and we have those an effective coding of ordinals in those blue intervals. So in the beginning we introduced the coding in between omega 1 and u omega. So similarly, using the EM blueprint formulation of the level 3 sharp, we will get an effective coding of all the ordinals in between delta 1,3 and lambda 5. And so in this next red interval, it will be similar to all those previous red intervals. So this picture will propagate through the projective hierarchy. And once again, there is a canonical way of, this is the normal form of pi15 sets. So it is pi15 if and only if it is sigma 1 definable over the least admissible set containing the level 4 Martin-Soloway tree, T4. So T4 is the canonical tree which absorbs the 4 additional quantifier in the pi15 definition. And we can similarly define the higher level Kleini's O, which enables us to continue the induction into the 5th and 6th level. So to recap, well, from inner model theory, we had those mice, 0 sharp, which is the least non-trivial mouse. And we have the least mouse with a sharp and 1 wooden, and 2 woodens, and 3 woodens, and so forth. And on the descriptive set theoretic side, we have a characterization. So 0, 2 sharp is the leftmost branch of the canonical tree. which is the Martin-Soloway tree, and 4 sharp is the leftmost branch of the higher level Martin-Soloway tree. And so for the other levels, they are the unique EM blueprints, the unique higher level EM blueprints. So from this, this equivalence will enable us to get an effective coding of all the ordinals which are below delta 1n for finite n. That generalizes the picture I had in the previous slide. And we will get the effectively Suslinness, and we will get a clear structural theory of all the projectively well-ordered cardinalities. So, so some related questions is that, well, assuming more determinacy, this picture should go beyond the projective hierarchy. And well, we know that sigma 1 over this structure will be the normal form for pi13 sets. But we still have very little understanding about the least admissible over T2. So on contrary to the other side, like, well, L is the least inner model and LT3 is just a mouse by a theorem of Steele. There is still a lot of misinformation about the levels, actually the even levels. Yeah. So, and so since this conference is about canonical structures, this is our canonical structure over T2n, and this is the canonical structure. So this sigma 1 definability over this will be pi1 2n plus 1, and sigma 1 definability over this will be sigma 1 2n plus 2. So the whole equivalent. So the whole point is to get an effective, so to get a deep structural understanding about those structures and the projectively well-ordered cardinalities. And I hope it will have many implications in descriptive set theory. So one application is that we can get the equivalence of determinacy for bold-face pi1 2n plus 1 and light-face pi1 2n plus 2 sets, and the existence of a mouse with a sharp and a 2n plus 1 wooden cardinals. So my hope is that that every theorem in descriptive set theory at the level of sigma 1 1 using sharps will generalize to the higher levels in the projective hierarchy, just because we have a very good understanding about those canonical structures or those canonical trees, and the structural theory about those projectively well-ordered cardinalities. So yeah, so I'm completing my paper. So the first half, which contains most of the key ideas, will be available on arXiv by the end of this year. Thank you for your attention.